of this series. Our speaker today is Hasan Eslami. Hasan is a PhD from the Environmental Infrastructure Engineering program. He's from the 37th cycle, if I'm not wrong. And he works under the supervision of Professor Alice. And his research is focused on sediment overload, on the effect of sediment overloading on channels. So with this, I just leave the floor to Hasan.
Thank you. Good evening, everybody. As Chiara mentioned, the title of my work is Investigation of Channel Aggradation due to sediment overloading. I'd like to start my presentation with these pictures, which are related to Sondrio, an event in Sondrio in 1987. The notable things in these pictures are the amount of the sediments deposited inside the river channel inside the city. Indeed, during the event, due to intense rainfall, a lot of sediments have been transported from the basin with a certain celerity inside the city and deposited there. Obviously, this amount of the sediment can result in a decrease in the capacity of the conveying capacity of the river in the conveying water that can consequently can result in a flood in the city. So these considerations and the events like this somehow improve the importance of the study of river sediment transport and possible aggradation process. This study can be done from different points of view. It can be studied mathematically, it can be studied experimentally in microscopic scales or macroscopic scales and so on. What I'm focusing on in this regard is are listed here, investigating the celerity of propagation of aggradation wave and the celerity of smoke perturbations, analytically and numerically simulating the aggradation process, dependency of aggradation celerity on the controlling parameters, and the effect of the presence of the sediment transport in a flow. All these investigations are done by performing aggradation experiments in hydraulic lab of Politecnico di Milano in Lecco campus. So before going in detail with these investigations, I'd like to introduce you our experimental setup. Our rectangular channel is made of an erodible bed with uniform sediment mixture of PVC. There's a hopper, as you can see here in the upstream part of the channel, that feeds the channel during the experiment. And also, as you can see, there is a tank through which the water gets into the channel during the experiment. Different parameters, including sediment inflow discharge, bed surface elevation, and water surface elevation, are measured by using different cameras and by applying image processing methods. So far, we have performed 19 aggradation experiments with the control parameters that are reported here in this table. Experiments are in 6 categories from the water discharge point of view, from Q equal to 4 to Q equal to 9, and are in 4 categories from the loading ratio point of view that you can see here. The loading ratio is the ratio between the sediment inflow discharge and the initial sediment transport capacity of the channel. In particular, I'm going to present you the results of one experiment, AE4, in this presentation with these controlling parameters. Having this detailed measurement of method for measurements, we are able to measure bed and water surface elevation in each time and space. In the top, for example, you can see the bed surface spatial evolution of bed in some specific times as the initial results of our campaigns. In the temporal spatial evolution of the water in some specific times, the temporal evolution of bed and water in some specific section. Also, as mentioned, using these measurement methods, we are able to produce a matrix showing in each time and space the bed and water surface elevation. that you can see this matrix as color gradient map in bottom. The left is related to the bed evolution, and the right is related to water evolution. After this introduction about experimental campaign and measurement methods, let's go on with the first investigation. As you know, when a channel is overloaded with sediment, an aggradation wave propagates with a certain celerity along the ridge. Knowing this celerity of propagation of aggradation wave is crucial from the hazard assessment point of view, because it is important to know when the sediment front reaches to a key spot. When the flow velocity is low, like this video that you can see, the sediment front is of translational type, where a sediment front is detectable, and one can use a tracing method in order to estimate this celerity. On the other hand, when the flow velocity is high, mostly in supracritical condition, the sediment front is dispersive type, where there is no sediment front to be detected. So, the question, one question that may arise here is that how can the celerity of aggradation wave be quantified when the sediment front is of dispersive type? To answer this question, we use the standard definition of the celerity of any quantity, and we applied this definition to our experimental data for the bed evolution, for the matrix of bed. We could find this equation in discrete form for this celerity, and finally, by choosing an appropriate delta x and delta t, we could quantify the local and instantaneous celerity of propagation of aggradation wave as color gradient map in dimensional form and in dimensionless form. It's worth mentioning that for the dimension, for normalization, we use the matrix of the flow velocity. Besides this aggradation wave, which propagates with a certain celerity along the ridge, there are the so-called small perturbations, which propagate with a certain celerities along the ridge. So then my next step is to quantify this celerity of small perturbation. To do so, firstly, a quick review of the mathematical stuff is needed. As you know, the hydromorphologic evolution of bed and water surface elevation in 1D condition can be depicted by a system of partial differential equation, including two Saint-Venant equation and one X equation, accompanied by two closure equations, one for estimating friction slope and one for estimating QS sediment discharge. That in this work we use Mayer, Petter, and Muller formula. However, this system can be written in matrix form, and what's important here for us is this coefficient matrix, because different studies have argued that the eigenvalues of this matrix represent the celerity of propagation of small perturbations in bed and water surface elevation. So, in order to find these eigenvalues, it's enough to solve this polynomial equation. Also, there is some exact solutions for this polynomial equation. Approximated solutions could be useful for interpretation purposes. In this regard, different studies, as you can see, have proposed different equations for these eigenvalues. And among them, we choose Gautier approach because it is valid, firstly, it is valid for entire range of the Freud number, and second, it has a very good consistency with these exact solution of the polynomial. After choosing this and applying this equation to our work, we could finally find these eigenvalues, dimensionless eigenvalues, as color gradient map, which represent the celerity of small perturbations in the propagation of small perturbations in bed and water surfaces. It's worth mentioning that in order to make eigenvalue determination fully consistent with the performed experiments, we calibrated this MPM formula by introducing two calibration parameters, alpha and n, that I will explain a bit in detail in the last part of my presentations. However, so far we have been able to determine the celerity of propagation of small perturbations and celerity of propagation of aggradation wave. Having a look at these graphs, one can say, especially to the average values, one can say that the celerity of propagation of aggradation wave is much smaller than the celerity of small perturbations, which is somehow consistent with the concept of the smaller, the faster. Despite this significant difference between these two scales of propagation, one question that may come to mind is that, is there any correlation between these two scales of propagation? We produce the correlation plots, and here you can see the correlation plot for these two scales of propagation. And discarding this part of the graphs, all of them, which is related to very initial part of our experiment where the bed has not been adjusted yet, one can say that there is a correlation between these two scales of propagation, so that the dimensionless celerity of aggradation wave increases with the dimensionless lambda 1 and lambda 2, absolute value of the lambda 2, while it decreases with the dimensionless lambda 3. Also, it's worth mentioning that lambda 1 refers to the water propagation of small perturbations in the water surfaces, while lambda 2 and lambda 3 refer to the small perturbations in the bed surfaces. The second part of our work has been devoted to analytically simulating the aggradation process. As mentioned, the governing equations for hydromorphologic evolution include two Saint-Venant equations and one external equation accompanied by two closure equations. Here you can see the schema of this evolution, this process. Different studies have tried to simplify these PDEs to just one single linear diffusion equation by applying some simplification, by applying, let's say, assumptions. The assumptions are listed here. The flow is quasi-steady, the flow is quasi-uniform, the friction factor is constant, and so on. However, by applying these assumptions and manipulating the previous PDEs, a linear diffusion equation was derived for the bed aggradation in the channel. And here you can see this equation, where this K is called the linear diffusion coefficient. Obviously, by solving this equation, one can obtain the bed evolution during a run for that experiment. So, in this regard, again, different studies have tried to find an analytical solution for this equation instead of solving numerically. Among them, Gill, by considering appropriate boundary condition and initial condition, could find two kinds of analytical solution for this equation: Fourier series solution and error function solution. We choose the Fourier series solution and we apply this solution to our campaign, to our experiment. The input of this solution, as you can see, is the L, which is the length of the channel, S0, which is the initial slope of the channel, S infinite here means the slope of the channel in the equilibrium time, and K is the diffusion coefficient. S0, S infinite, and L can be obtained during the experiment using image processing methods. But for the K, we used for the initial value of initial estimation, the equation proposed again by Gill that you can see here. QS0 is the initial sediment transport capacity of the channel per unit width. Q infinite is the sediment transport rate per unit width in the equilibrium time, which would be equal to the sediment inflow discharge, that we are able to obtain it using PIV algorithm, for example. However, by applying this equation, this solution to our work, we are able to obtain the analytical solution in our campaign for each experiment after applying. Again, you can see here the analytical results for spatial evolution of bed and for temporal evolution of bed. The next step is to compare these analytical solutions with the experimental profiles. And as you can see, they are not consistent with each other. So in order to make consistency between the results, we should calibrate the analytical solution. And in this regard, the calibration parameter would be K, that is the diffusion coefficient. After several trials, we could calibrate it, and this is the previous comparison after calibration, that now there is a very good consistency between the results. Also, you can see the comparison between the color gradient map of the bed between experimental result and analytical result. As you can see, this analytical one has been applied until the equilibrium time. However, having this solution, Fourier solution for Z, one can, we apply the standard definition of the celerity on this solution also, and we could obtain the celerity for analytical solution like this formula. And here you can see again the comparison between experimental celerity and analytical one. The procedure performed for all the experiments, and in this table here you can see the diffusion coefficient for all the experiments, the calibrated one, the one coming from the Gill formula, their relationship. And here you can see the relation between K coming from Gill and the calibrated one. As you can see, for some experiments, the equation proposed by Gill works very well, but for some others, it doesn't work very well. The reason may refers to the fact that this analytical solution has been derived using different assumptions. But anyway, we could found in this part that with just constant value for K, we are able to reproduce the bed evolution during entire of the experiment. This K varies from one experiment to another experiment. So another question rises here, and that is, does this diffusion coefficient depend on the controlling parameters? Honestly, we have arrived in this point now, and nowadays we are working on this part. So unfortunately, I do not have answer for this question for the time being. We are now working on it. In the first part of my presentation, I talked about the celerity of propagation of aggradation wave during one experiment. And we found a correlation between this celerity of aggradation wave and small perturbation, again, during one experiment. The aim of this part is to find a representative value for the celerity of propagation of aggradation that present the celerity corresponding to each experiment. After finding this representative value for each experiment, we put these values in a graph against the controlling parameters and to find out what's the dependency of this celerity on the controlling parameters. So in the first step, a method should be used to derive average from the color gradient map of the celerity of aggradation wave. The reason that we did not consider all the color gradient map of the celerity for the averaging is that during each experiment, time passing through the bed aggradation increase until a specific time. That is equilibrium time, where we do not have the aggradation anymore. Since we do not have aggradation anymore, we do not have celerity. After that part, you can see this zero region in this picture that is here. Also, you can see this equilibrium time, that is this dashed line, in the color gradient map of bed, where the counter lines becomes vertical. That means there is no aggradation anymore. So the region that we are interested in would be this region, where we are before equilibrium time and the celerity is not zero. But the question is that which part of this color, this region, should be considered for averaging process? To answer this question, we use the analytical solution. And here you can see the color gradient map of the celerity obtained from analytical solution. Indeed, these control lines show somehow how this aggradation wave in analytical solution propagates towards the end of the channel. And so this dashed line somehow shows the time at which the aggradation wave of the analytical solution reached to the downstream part of the channel. This time can be calculated using this equation, again proposed by T. And actually, we used this time for our experimental results. And we applied, indeed, this time for our experimental results. Based on this time, we consider two scenarios. In the first scenario, you can see that we considered this triangle for averaging process. You can see in the experimental work. And in the second scenario, we mirrored this triangle that you can see here. As another example, you can see this averaging area in our color gradient in other experiment. The region that we have considered for averaging process. After doing this job for all the experiments, we could obtain one representative value for the celerity corresponding to that experiment. We divided it by U, the theoretical water velocity, and then we put it in the graph against the controlling parameter, loading ratio, and fruit number. First of all, as you can see, there is not that much difference between two scenarios, considering one triangle or two triangles. Second, as you can see, the dimensionless celerity is an increasing function with respect to the loading ratio. Third, you can see that there is no evident effect of the fruit number on the celerity. The reason refers to the fact that it's right that we have increased the Q from 4 to 9, but since our reference slope was constant during all the experiment, the fruit number does not change that much. And you can see the range of the fruit number that is somehow constant, 1.2 to 1.25. That's why we are not able to see an evident effect of the fruit number on the celerity. And the final point regarding this slide is that could be useful for practitioners is that the maximum average value of this dimensionless celerity is 0.03. The final part of my presentation is related to numerically simulating the aggradation process and the effect of the presence of sediment transport in a flow. I'd like to start this part of presentation with a question. What is the effect of the sediment transport on the flow resistance? Several studies have debated on if and how the presence of the sediment transport may change the flow resistance. In this regard, some studies have found that the presence of the sediment transport can result in an increase in the flow resistance. Like this graph that shows the injection of the sediment in the clear water condition can increase the friction factor. On the other hand, some studies have found that the presence of the sediment transport can result in an increase the flow velocity, like the graph in the right part. So the aim of this part of my presentation is to contribute to the issue by investigating an equivalent Manning coefficient. To do so, the laboratory results of the experimental campaign were numerically simulated using a numerical solver that is called Basement, developed at ETH Zurich. Here you can see our simulated experimental canal, our simulated channel. Also, it's worth mentioning that the geometry and sediment parameters were simulated were exactly the same as the experimental ones. We used two boundary conditions, upstream boundary condition, one for sediment feeding rate. That is this graph that is coming from a PID algorithm and using a transfer function. Another is the water discharge, that is this one. That is coming from analyzing the data coming from the laser installed in the tank. However, as you can see, for the first, for the initial value for the Manning coefficient, we used the one coming from the clear water condition. That is 0.050. After simulating and building the model, we run the model, we obtained the model, and we compared the profiles, the numerical profiles, with the experimental ones that you can see here. Now, again, you can see that there is no consistency between experimental profiles and numerical ones. The ones coming, let's say, from the simulation. So we found out that in order to make consistency between the experimental and numerical results, two parameters should be calibrated. One is the bed load factor alpha, that mostly affects the bed profile, and another is Manning coefficient that mostly affects the water profile. After calibration, we could we compared the results, and here you can see comparison after the calibration, and there is a good consistency between the profiles, as you can see. The procedure we perform for all the experiments. Here you can see the amount of the alpha and n obtained for each experiment, and in the last column you can see the dimensionless Manning coefficient can be calculated using this equation. And at the end, we plotted these points, these alpha and n, against, again, controlling parameters like loading ratio and Froude number. Having looked at this graph, one can say that there is an increase in the equivalent Manning coefficient due to the presence of bed load transport. That is somehow consistent with some studies saying that the presence of the bed load transport can result in an increase in the flow resistance. Also, having looked at again these graphs, one can say that this increase, while it does not depend on the loading ratio, it depends on the Froude number and water discharge. So that for the experiments with higher water discharge, we can see a lower increase in the Manning coefficient. Also, having looked at these graphs, one can say that this alpha bed load factor is an increasing function of both loading ratio and Froude number, and you can see this increasing function. As a summary, you can see here the list of our findings related to each part of our work that I mentioned during this presentation, and due to time limitation, I do not like to repeat all the points. So I skipped this slide, but these are the points I've mentioned during the presentation. And here you can see the list of works that we have published or submitted or presented in different journals and conferences. And it's worth mentioning that regarding the second part of my work, our work, there is possibility to publish one or two another journal paper. And the last slide of my presentation is related to the prospects. We are now planning to do experiment with higher fruit number, with changing the slope of the channel to see the effect of this fruit number on the parameters like celerity of propagation of aggradation rates. As I mentioned, also we are working on investigating this dependency of the diffusion coefficient on the controlling parameters. We are conducting a dimensionless analysis of bed channel. Here you can see the temporal evolution of the bed channel regarding each experiment and each category of the loading ratio. And we are going to do dimensionless analysis on this bed channel to finally fit one equation to predict the slope during each experiment and probably to find the final equilibrium slope. And finally, we want to provide a unified view of all these aspects that I mentioned. We could find some findings regarding each part, but final step of our work would be devoted to provide a unified approach for all these processes that could be useful from the engineering point of view and could be quantitative tools for practitioners. Thanks for your attention and patience.